The first 2024 special video will be released this November. Stick around at the end of this video to learn more. The universe is unfathomably complex in every way imaginable. Even if the observable universe, which is an expanding sphere 93 billion light-years in diameter, is only a small fraction of the actual universe, it is impossible for our brains to even picture the scales that we are dealing with. Today, let's freeze time and travel back to the moment when everything started. The Big Bang. Timeline of the universe. For now, we're not going to talk about the Big Bang itself, or the period immediately afterward, because our theories kind of become icky there. From 10 to the minus 43 to 10 to the minus 35 seconds after the Big Bang, the universe was in what's called the Grand Unification Theory epoch. Appreciate the beauty of this moment. The entire universe, estimated to be 10 to the 32 Kelvin, was orders of magnitude smaller than an electron. It was so hot that no particles could exist. Everything in existence was in the form of blazing energy and radiation. The epoch began with a separation of gravity from the other three fundamental forces of nature: electromagnetism, the strong and the weak nuclear forces. In other words, the universe can now be separately described by quantum mechanics and general relativity. At 10 to the minus 35 seconds after the Big Bang, the strong nuclear force separated from the other two fundamental forces. Scientists think this triggered cosmic inflation, a short but exponentially rapid period of inflation that expanded the radius of the universe by a factor of 10 to the 26. To put inflation into context, it's like the universe expanding from the size of an atom to the size of the solar system in a thousandth of a second. The specifics of the inflationary epoch are still unclear, but we know that inflation ended around 10 to the minus 32 seconds after the Big Bang because of a critical drop in the energy density. At this point in time, called the electro-weak epoch, electromagnetism separates from the weak nuclear force. We finally have something that resembles the modern universe. The four fundamental forces of nature are distinct from each other, and the force-carrying bosons have emerged. This epoch ends at 10 to the minus 12 seconds after the Big Bang, with temperatures that have plummeted from 10 to the 28 Kelvin at the start of the inflationary epoch to 10 to the 15 Kelvin at the end of the electro-weak epoch. The universe is now about as large as the orbit of Venus. From 10 to the minus 12 to 10 to the minus 6 seconds after the Big Bang, we enter the quark epoch. Quarks, leptons, and their respective antiparticles formed a thick, dense 10 to the 15 Kelvin soup called quark-gluon plasma. We've already talked about the state of matter in a previous video. Because particles were moving with so much energy, large matter particles like hadrons couldn't be formed. Throughout the quark epoch, matter and antimatter pairs of particles annihilated each other upon impact. For some reason, the universe did not create an equal number of matter and antimatter particles. For every billion antimatter particles, 1 billion and 1 matter particles had been formed. At the end of the quark epoch, the universe was predominantly made of matter as a result of the imbalance. The Hadron epoch began after the great matter-antimatter annihilation, and temperatures dipped to 10 to the 10 Kelvin by the end of the period. Particles finally lose enough energy so that they can combine to form larger structures. Quarks bind together to form protons and neutrons, the building blocks of atomic nuclei. Congratulations, everyone! The universe is now 1 second old. The sphere that will soon become the observable universe is now 20 light-years across, the distance to Earth's stellar neighborhood. Neutrinos and antineutrinos, tiny elementary particles, now stop interacting with matter in what's called neutrino decoupling. Because neutrinos pretty much don't interact with anything, these neutrinos are still around in the universe today, forming what's called the cosmic neutrino background. This cleanly leads to the lepton epoch, which stretches until 10 seconds after the Big Bang. Leptons, the family of subatomic particles that the electron belongs to, dominate the universe in lepton-anti-lepton pairs, which were sustained by the lasting energy of photons. By the end of the lepton epoch, when temperatures decreased to 10 to the 9 Kelvin, the universe was left primarily with leptons. The radiation-dominated era of the universe's history draws to a close with the nucleosynthesis epoch, which lasted from 10 to the 3 seconds, around 16 minutes after the Big Bang. The plasma filling the entire universe, cooling from 10 to the 9 to 10 to the 7 Kelvin, is made up of charged atomic nuclei, electrons, and radiation in the form of photons. The ratio of hydrogen to helium nuclei that are present is in the ratio of 3 to 1, which is pretty much the same today. As the universe now has a radius of 300 light-years, the density has plummeted to 4 grams per cubic meter, 0.3% of the density of air at sea level. As temperatures and density continue to decline, the nuclear fusion of hadrons will soon no longer be possible. The nuclear synthesis continues into the photon epoch, which is basically a loosely defined stretch of time that continues on until 380,000 years after the Big Bang. Temperatures dive to a measly 4,000 Kelvin, while the radius of the observable universe increases to around 42 million light-years, several times wider than the local group. During this epoch, recombination happens. Temperatures are finally low enough to allow nuclei and electrons to combine to form the first atoms. Recombination also marked one of the most important transitions in the universe. Photons don't interact with neutral particles, so the atom-filled universe became transparent to light. Empty space was finally dark and transparent, as it is today. The light that was released during recombination forms the cosmic microwave background today, an early relic of the universe that was one of the strongest proofs of the Big Bang. We've now entered the Dark Ages. The universe is cold and devoid of visible light. Leftover CMB photons are severely redshifted to the infrared, and temperatures are now only 60 degrees above absolute zero. Physicists estimate that around 100 and 200 million years after the Big Bang, the first stars were formed, ushering in the reionization epoch. In the course of all stars, hydrogen is fused into helium, releasing a tremendous amount of energy. Eventually, due to the gravitational attraction between stars, the first galaxies form, having supernovae that seed the universe with heavy elements. As the expansion of the universe continues on, galaxies coalesce into galaxy groups home to tens of thousands of galaxies. Finally, a whopping 13.8 billion years after the Big Bang, we reach the present day, the evolution of the universe. Even though gravity has stitched the universe into coherent galaxy groups, the expansion of the universe is accelerating in the vast stretches of intergalactic space. We don't know why this is happening, so scientists created a new force called dark energy. In the current universe, around 3/4 of the mass energy content is this dark energy. Based on our current understanding of cosmology, in the near future, dark energy will cause space to expand at an ever-increasing rate. In a few 100 billion years, everything outside of the local group will be receding away faster than the speed of light, permanently isolating galaxy groups from each other. The birth of existence. So earlier, we glossed over some important details of the birth of our universe. The Planck epoch is the brief moment of time from the Big Bang to 10 to the minus 43 seconds afterwards, when all 4 fundamental forces of nature were united. There's no other way to put it. We have no idea what's going on here. The universe at this stage was infinitely hot and infinitely dense, and our laws just don't make sense in this environment. Describing the Planck epoch would require unifying general relativity with quantum mechanics, and we've already gone into that problem in a previous video. You can go check out the links in the video description below. Essentially, we can describe everything right after the Planck epoch with relative certainty. But what about the Big Bang itself? Traditional models describe the Big Bang as the moment when the entire universe, space, time, matter, and energy are created from an infinitely dense point called the singularity. We don't know why the singularity existed, what happened before the Big Bang, or what caused the Big Bang. In fact, in recent years, some physicists have questioned whether this view of the evolution of the universe is accurate or not. But as of today, this is everything we know about the universe so far. Conclusion. Now it's time for a groundbreaking announcement, the release of the first special video of 2024. This year's special video is a continuation of our video from 2022 on genetic engineering. This time, we're diving into the nitty-gritty science behind designer babies and biotechnology. While our 2022 special video gave a sweet introduction to DNA and the ethical implications of gene editing, this year's edition is the long-awaited sequel to the enigmatic science involving playing with molecules. We are aiming for a release date of November 29th. Stay tuned to the channel and our website to learn more. More details and special announcements are on their way. Thank you for watching the Information Institute.